Okay, so we're going to be talking about a type of word problem where we do just what it says there, determining the molar mass of a solute using boiling point, elevation, and freezing point depression information. Okay, so here is the question. Find the molar mass of an unknown non-volatile molecular solute if the solution begins to freeze at negative 0.186 degrees C. The solution was prepared by dissolving 1.8 grams of the unknown in 1,000 grams of water. Now, there's a couple of interesting things about this question that I want to make sure I point out to you. If you take a look at what I've written here, I said it was a non-volatile molecular solute. And the important thing about that is that it always has to be this situation. The reason why non-volatile is important here is that something that's a volatile solute would evaporate very quickly and would get out of the water, even though it would be potentially dissolved in it, it would actually leave the water at a higher rate than the water would leave. So this has to be something that is going to, under most circumstances, stay dissolved in the water. If it didn't stay dissolved in the water, obviously it's then going to change, and the water is eventually going to have nothing in it, and it'll just be like water. And then it's a molecular solute because, as you know from our last screencast, when we talk about something that's a molecular solute, then the concentration isn't going to change because the number of particles is going to be the same as the number of moles of the substance that you had in the first place. Since it's a molecule, when it dissolves, it still stays as a molecule. It does not ionize. So having that phrase in there that I've underlined in blue seems a little bit wordy, but it's really vital so that you understand what it is I'm looking for. I would never be able to ask you this if it was an ionic compound. Okay, so how do we go about doing a question like this? I'm going to move up a little bit here. Hopefully I won't run out of space too much here. The first thing that you should recall, or I might not be able to you might not be able to recall it, but that is that, whoops, that's not what I wanted to write. Go away. Okay. That the Kf for water is 1.86 degrees C per molal, right? So if we know that that's the case, and we also know that if we have our equation for freezing point, it looks like this, right? And if we know that the temperature dropped from 0 degrees C to negative 0.186 degrees, we know that that's our delta TF. Okay. Now you only need to take the absolute value of the delta TF. So I'm just going to write positive 0.186 because it's a change there, degrees C. And of course, since I just gave you seconds ago that the Kf of water is that value, I can go ahead then and insert 1.86 degrees C per molal, and then that's what we're going to be solving for, right? The molality of this situation. And when we do that, we find that, that the molality is 0.1000. Oh, no, too many zeros. Okay, 3 sig figs here. Actually, is it 3 sig figs? Yeah, 3 sig figs, 1.80. And then we also know, too, that if that's our molality, in general, we know that molality is the number of moles of whatever solute you're dealing with divided by the number of kilograms of the solvent, which in this case is the water. And we have that information because in terms of the number of the solvent, the number of kilograms of the solvent, we have that you have 1,000 grams of water, which is equivalent to 1 kilogram. So I can go ahead, let me just do equals here. I have 1 kilogram of my solvent, which is water, and I don't know what the number of moles of solute is. So that's my X value, the number of moles of my solute. However, I do have my molality, so I can, instead of putting just a blank old M there, I know that my molality is 0.100. If that's the information, then I can clearly do everything to solve right there for my solute. And when you solve for your solute there, it's pretty easy math, I would hope. You would find out that you have, well, I got to move to a new page here. Okay, I just have to copy and paste it to a fresh thing here. When you solve for x here, you find that the number of moles of your solution is going to be 0.100 mole, not solution, Chang, you idiot, moles of solute. Okay, so that's the number of moles of solute. And you also know that you added originally 1.8 grams of that solute. Right? That's an important thing because I gave that to you in the question. So that means if I have 1.8 grams of the solute here, that is the same as 0.100 moles of our unknown solute. Right? That's what I just calculated here, so those must be equivalent things. And if I want to know how many moles, what the molar mass is of the substance, then it's simply the number of moles. No, I'm sorry, it's the number of grams per the number of moles. So all you need to do is take the 1.80 grams, divide that by the number of moles, right, as your equivalency. But of course you want an entire mole, you don't just want 0.1 mole, so if in some ways it's sort of odd, but this is what it would look like if you were multiplying the number of moles you want by the equivalency. And when you crank that out, it's 18 grams per mole. That is, folks, the molar mass of the substance that I dissolved into the water. Okay? So there you have it. It's a fairly straightforward process. I want you to make sure that you go back and look at this carefully so that you can understand how we arrived at that solution, because you can probably do this mechanically, but to understand how we actually got it is what's more important. Bye.